Hi, welcome to another week of the data engineering course. This week, the main topic is on visualization, and I propose I start with a small recap of last week on NoSQL. So, a small summary. So we saw data warehousing and analysis. So the purpose of a data warehouse is to provide decision support based on historical data. So for instance, a company might see its revenue drop compared to last year, and then they might be interested in looking at the data and see what's going on. So maybe the problem is local to some branch, so they can slice the data only on that branch, or they can, maybe the problem is with some type of product that sells less compared to last year, so they can then maybe create a pivot table showing the number of sales for that product over the different quarters each year, things like that. Very essential to many businesses. There are different systems to do that. So you could use the operational relational database. However, that has a number of issues. For instance, these queries, they typically aggregate over all data. So if you then have a transaction in an online system, then these transactions might lock parts of the data. And then if you, in parallel, do a big query on all data, that becomes really a bottleneck. So that's not a good idea. So what can you do? You can extract data from your different data sources. So it might be different relational databases, for instance, for each department, and create one big database, a data warehouse that contains all historical data. You can use a relational database for that. So we call that relational OLAP, where OLAP stands for online analytical processing. You can use a system that internally uses data cubes, or you can use an SQL on everything system, such as Google BigQuery, which scales if you have gigabytes or even petabytes of data. Typical operations are pivots. So pivoting means selecting two dimensions of interests and then looking at the counts in that two-dimensional space, and also the marginals. So that's one option. Another option is to slice the data, so select a subset of the data based on a certain year or a certain product type, for instance. Then you can drill down on a dimension. For instance, you might look at average sales over an entire year, and then drill down to quarters, then drill down to a certain month or week even. And the inverse is roll up. So roll up, if you're looking at a quarter, and then you can roll up and look at the total sales on a yearly basis on something like that. And you can drill down and roll up on different dimensions if they're hierarchical. For instance, location is typically hierarchical, where you have the continent, country, city kind of hierarchies, or even products. You might have product types, which is more general than maybe subtypes, and then individual products. Often with such an OLAP system, you represent the data as using a star schema. So that means you have one central fact table, which maybe is the amount of purchases, or the central fact, or the amount of shipments, something like that. And then you have different dimension tables. And so each dimension is a separate table, and it has the shape of a star. That's why it's called a star schema. And so dimension can be the product type, or location, time, the salesperson, end user or customer, things like that. And then finally, we saw what denormalization is. So typically in a relational database, all attributes are stored in a separate table, and that's easy. because if you want to update the data, for example, you want to update the name of the supplier, you go to the suppliers table and just update that column. And if there are shipments of that supplier, it links with a foreign key to the supplier table. And so all shipments of that supplier will share that name. You only store the name in one row. While for analysis, you usually want to denormalize the data. So that means you create one huge table where you include all information of all the different dimensions. So that's for analysis, you usually want, like 10 or 20 or 30 columns all in one table. So you did some exercises with pandas, with Raphael. So you transformed a single series, is it called in pandas, or columns. You can transform them with map or apply. You can also aggregate columns using all the classical function, the minimum, the maximum, sum, mean. There are several options to transform a data frame as a whole. For instance, group by, where you group on some column, and then you count or sum values based on each group, of all rows in each group. You can pivot a table. And there are also several operations to combine different data frames, like merge. It's like a join in SQL, where you join several tables based on some columns in both tables where you want the value to be equal. So it's like an intersection. Append is just stacking different data frames. For example, if you have a data frame containing all data of January and then another one of February, but they have the same columns, you can just append them, and then you just add all rows vertically, or you can also concatenate two data frames. And there you do it horizontally. So there you append, but all columns, the new data frame will contain all columns of both original data frames. So that's about data warehousing. And then we saw NoSQL, or not only SQL. There are four main types of NoSQL database. Databases, key value stores, such as Redis. So a key value store is basically a distributed key value map. So a little bit like a dictionary in Python, where you have a simple key and then you store a value associated with that key. Typically, different value types are supported. It might be small maps or lists or sets of values. And a typical application for key value stores is caching. And so caching means storing some computation that you then can reference from the cache. So usually these values are stored in memory, and you can quickly retrieve them using a key value store. You can also store something like a user profile, where you have the name and a couple of attributes about each user. You can associate them with a unique key for each user, things like that. Then the second type of database we saw were document databases, and you also did some exercises on that with MongoDB. So with MongoDB, you can easily store and retrieve documents stored in JSON or XML. And then a third type of database, also based on the aggregation principle. And so where you have a group of or an object of properties, and you don't want to be joins, so you store that piece of data together. So that's an aggregation-based principle. And a column-oriented database stores data into rows and column families. So the main difference is that in each column family, you can store up to, I think, 1 million of columns. And the data is partitioned on two levels. So it's partitioned into rows. So for instance, in Google Bigtable, you store typically you store a couple of gigabytes of rows, and it's called a tablet, and it's stored on a different machine if you have millions of rows, and then it's organized like that. Often they also support versioning. So with versioning, that means if you update a value for some column, that you also keep the previous version of that value, so that you have a kind of timeline of all the changes of one attribute. And then finally, we have a kind of special database, which is a graph database. And an example system is Neo4j. And there, each instance, so each row, if you want, is a node. It has a number of properties, and it's connected through another node using an edge. And an edge can also have some properties. So these are the 4 types of systems. So they emerged by the need to process really web-scale data sets. So these are data sets that don't fit on a single computer, petabytes of data, and you have a cluster of 10 or hundreds or thousands computers working together, and that store that and are able to store and process those types of data sets. So an important requirement for that software is that the cluster continues to process data or store data despite computer or network failures. So that's an important requirement. And Google was a pioneer in that type of systems, and they invented Google File System, which was later open sourced as Hadoop File System, MapReduce, and MapReduce allows you to write programs with map and reduce functions, and these programs can then be run on a cluster and really process petabytes of data. Bigtable, mentioned before, the column-oriented database, and also Dremel, which is used for online analytic processing. So Google was really a pioneer there. Then we saw the Cap Theorem. So the Cap Theorem, in essence, means you have consistency of the data, which means the same value of some row is consistently stored everywhere. So, for instance, if you store balances of bank accounts, you want that to be consistent. You want the same balance on different possible machines inside your cluster. Then you have availability. So availability means that you can always retrieve some data. Might not be the latest version, so it might be that it's a slightly outdated value that you read, but you can always read it. You never have to wait, and that also means it's replicated on several computers in practice. And then finally, partition tolerance means the tolerance towards failure. So you can have an individual machine that fails, or you can have a subnetwork that fails for some reason, that a couple of machines or racks even are no longer accessible over the network. And so the Cap Theorem basically says choose 2 out of these 3 properties. And you cannot have a system that has all 3 properties. You have to design your system so that you have 2 out of 3. And for a database, that usually means the focus on consistency and also availability, but not on partition tolerance. And so these newer NoSQL systems, they make a different trade-off. So maybe for Twitter or Facebook, you don't have the latest messages of another users, but these systems are always available. So they have a high partition, and they have a high partition tolerance. So I don't think Facebook has ever been down the last year. So they do that by leveraging not only SQL data storage. And finally, most of these systems use a combination of sharding and replication. And so with replication, if you have some data rows, you replicate them over all the different computers in your cluster. And with sharding, you separate your data. Maybe you have 10 rows, and then you store one row on one machine, second row on another machine, and so on. And so if you only shard or only replicate, then there are some issues. But if you use a combined approach, then you can allow for systems that are scalable. And so that means you don't copy all data to all machines. And so you partition your data and store it on some machines. You can also ensure a partition tolerance. For instance, you can copy each data block on at least 3 nodes. And if then one node fails, that's not a problem because you still have it stored on 2 other nodes. And finally, availability. So often a row is available on at least 1 node. And typically these comes at the cost of consistency. So that's a small summary of last week. Any more questions about this topic? I'm opening the chat now. No questions? Okay. Okay, then I'll continue with the main topic of today.